Hi everyone, welcome back to Causality with Boris, broadcast from Sobolev Spaces. In this video I talk about mediation formulas. Confounding free mediation and three cases of confounding are the main topics in today's lesson. Now, be sure to watch until the end and compare the takeaways with your notes. I've prepared extra material for this video. Click the link in the description and it will be sent to your inbox. Causal analysis is about treatment groups comparability. The control group and the treatment group should be as similar as possible, so we can be confident any effects are from the treatment alone. We compare treatment responses in carefully designed strata to ensure we are comparing like with like, with the only difference being whether they received treatment or not. Causal mediation analysis extends this approach beyond factors that can cause covariation between treatment and outcome. Once the mediator comes into play, we have to worry about other confounding factors. We looked at factors that can affect both treatment and mediator, as well as factors affecting mediator and outcome, but I would like to begin with the simple case of confounding free mediation. It reveals the structure of the estimation formulas, and it will be useful when confounding is in place. Let's take a look at what's known as a basic mediation diagram. Here you see three nodes: treatment T, outcome Y, and mediator M. The arrows show the two causal paths. There is an arrow between treatment and outcome. It means changes in treatment change outcome directly without a mediator. That's a direct effect. Or the effect can be indirect and mediated. At least part of the treatment effect is through changes in the mediator. Here's the key assumption. The direct and indirect effects produce the total treatment effect. The total effect describes changes in outcome due to changes in treatment transmitted through all causal paths. These three are the subject of the causal mediation analysis: total effect, direct and indirect effects. Take, for example, the natural direct effect. It's the expected outcome after applying treatment when mediating factors considered at the value they would take in the absence of treatment. We contrast two counterfactual situations: all units without treatment and all with treatment but with mediator values naturally occurring in the treatment absence. In the case of confounding free mediation, we estimate the direct effect in two steps. We simply take the difference between the mean outcome in treated and untreated groups, and then average it over the proportion of mediator values in the untreated group. Why exactly in the untreated group? Well, averaging in the untreated group gives us the expected outcome if everyone was untreated, and it standardizes the outcome in the treated group for the mediator distribution in untreated population. Let's take a look at treatment outcome and mediator coded as binary variables. I'll show how to estimate mediation effects directly from a frequency table. Here's the table. It presents stratification by three binary variables. They can be either 0 or 1. Combinations of their values define 8 strata. Each of them has its own number of study units, and I denote it as n from 1 to 8. The last column shows the proportion of untreated units with a mediator present relative to all observations in the untreated group. The mean outcome is just the probability that y is 1, and it can be estimated by the proportion of units with outcome 1. The table shows 4 proportions for each combination of treatment and mediator values. Using the last two columns, we can find the natural direct effect. We simply sum the difference in proportions between treatment groups at each mediator level, weighted by mediator prevalence in the untreated population. The next slide shows the results of the calculation for some hypothetical data. Let's say they describe the occurrence of complications and postoperative deaths by timing of surgery. The proportion of surgeries resulting in deaths increases with complications, and both complications and mortality change with time to surgery. And we wonder if complications explain variation in mortality by timing. Let's first find the total effect. This is the expected change in outcome after applying treatment when treatment changes the mediator in each unit. Expressed as the difference in marginal risks, the total treatment effect is the reduction in mortality by 3 cases for every 1,000 operations. Then we again calculate the expected outcome, but this time we keep the mediator at the levels it takes in each unit of the control group. The natural direct effect is a decrease of 2 deaths for every 1,000 operations. Then we compare the direct and total effects. We can say that 2/3 of the total effect of early surgery on postoperative mortality is due to the direct effect of timing. Let's add one confounding variable to the basic mediation diagram. This is a common cause for treatment and outcome, W3 not here. Here comes a crucial assumption. Condition on the single node makes all 3 effects identifiable. In practice, it may look like this diagram here, with all arrows removed from the conditioning set. You can recognize a basic mediation diagram here as well, relationships between timing, complication, and mortality. The mediation formula here resembles the typical adjustment formula. We average the direct effect in each stratum over the strata prevalence. There is, however, an important difference from the usual formula. We are weighting over the mediator prevalence as well now. Another important departure from the basic mediation formula. The conditional means depends on conditioning set now. So far, we added one confounder. Let's add more. This diagram shows a separate confounder for each relationship. Note W1 is the common cause for mediator and outcome. W2 is the common cause for treatment and mediator, and W3 is the common cause for treatment and outcome. Again, we make a crucial assumption. Conditioning on combination of these nodes makes all 3 effects identifiable. In this case, the mediation formula looks somewhat confusing. We are still averaging the natural direct effect in each stratum or the strata prevalence, and strata are determined by a combination of all 3 covariates. At the same time, conditional means and mediator proportions are conditioned on different covariates. This example shows just one common variable W which confounds all 3 relationships. You can see 3 arrows from the W node going to treatment, mediator, and outcome. In this case, the mediator formula is a stratification adjustment. We estimate the natural direct effect in each stratum defined by W and average over the strata prevalence. Just one more thing. Mediator is an outcome of treatment, and we couldn't possibly use it in regression adjustment for the total effect. Here, we put the mediator into the conditional means to block the indirect causal path. This leaves only the direct effect. In this chapter, I link the mediation and stratification formula using the idea of direct standardization. To do this, we need only 4 types of aggregate data. First, the number of observations in strata S and group G. It's small case n with 2 subscripts S and G. Second, the number of observations in stratum S. It's small case n sub s. Third, the number of observations in stratum S, group G, and the mediator level m. It's small case n sub s, g, and m. And fourth, the number of outcomes in stratum S, group G, and mediator m. It's small case n, s, g, m, and superscript 1. And of course, the uppercase n is the total number of observations. So how do we get the marginal risk among the treated with the mediator level for the untreated? Suppose the mediator variable encodes the presence and absence of the mediator as 1 and 0. We take the proportion of outcomes in treated units with and without mediator in each stratum. Next, we take the proportion of untreated units with and without mediator. Then we need the strata proportions in study population. We multiply these 3 proportions and we sum up the products from each stratum. To see the relationship to direct standardization, Let's rearrange the formula. To make it look like an inverse probability weighting, we take the inverse of the untreated proportion outside of the brackets in each stratum. What's left in the brackets? It's the expected number of deaths in the treated group, which we standardize by the presence of the mediator in the untreated group. I use word standardize in epidemiological sense. For direct standardization, we calculate the strata-specific rate in one population and apply it to a population with standard strata prevalence. Here we use the composition of mediator levels in the untreated as a standard population. We then stratify it by the adjustment covariate, and then we apply rates from corresponding strata of the treated group. As a result, we get the expected number of outcomes in the treated group standardized by the composition of mediator levels in the untreated group. Weighted by the inverse of the prevalence of untreated in each stratum and averaged over the entire study population, it gives us the counterfactual risk of outcome among the treated units in the presence of mediators typical in the untreated. Sounds like classical epidemiology. So here's the main message. In causal mediation analysis, we may need to account for three types of confounders. We account for factors that influence treatment and outcome, treatment and mediator and outcome. You learned that in confounding free mediation, we simply take the difference between the mean outcome in the group with and without treatment and average it over the proportion of mediator levels in the group without treatment. Don't miss the key connection between epidemiological standardization and mediation formula for natural direct effects. You watched another episode of Causality with Boris. Keep on watching.